All right, hello physics fans. Last time we talked about the simple harmonic oscillator, and today we're going to first apply the simple harmonic oscillator to a couple of sample systems. For instance, planets, believe it or not, can be described as simple harmonic oscillators where you have oscillator in X and in Y. And bridges, things like that. And then finally, our important thing that we're going towards is trying to move to the description of waves. Okay, so where did we get to last time? Well, last time we had this description of our harmonic oscillator. We had X that's changing in time, so this object is just going back and forth and back and forth. We had some period, which was the amount of time it takes to go from its maximum displacement back to equilibrium to the minimum displacement, or I guess to the minus maximum displacement, back to zero and up to our maximum. So it's in our picture, if we had our X versus T, this would be going all the way from our X max to our minus X max, that takes half of the period, and then back up to X max, and that is one period T. Then, if we wanted to find out how many of those cycles you get every second, you would take 1 over T, so the frequency is 1 over the period, or instead we could say the period is 1 over the frequency, same difference. And then the quantity that goes inside of the cosine here is actually 2 pi times the frequency. So omega is 2 pi times the frequency. And the reason we need to do that is because cosine is a function that repeats every 2 pi. So if we want this to fit in right, we have to put in that extra factor of 2 pi. Now the amplitude, we needed to be careful because our object is bouncing between X max and minus X max. Okay, so it's really half of the total span of that oscillation. So this is the distance between these two is 2 X max, and the amplitude is half of that because we're assuming that we're going around the average value of the oscillator. Then probably the most difficult part to understand is the phase of the system. The phase is just this number in angles that we're putting as the argument of the cosine function. Here, my phase would be 0. Halfway through, my phase is just pi, and then when I come back to the same position where I started, my phase would be 2 pi. So that's the same thing that's being said here. You start at 0, at pi over 2, you're moving backwards as fast as you can go, and then you start slowing down. At a phase of pi, you're at minus x, then you start going forward again. And then at 3 pi over 2, that's right here where you're crossing the 0 again, and then you go back to your x max at phase of 2 pi. Now, we also realized that because we know how calculus works, if we have this description for our x at time t, we can derive the velocity by taking the derivative. And what that does, by our chain rule, it brings out a factor of omega out front. And because we've got that factor of omega, we get an omega squared out front for the acceleration. Okay? And so what this allowed us to do was say that the acceleration for a simple harmonic oscillator is equal to minus omega squared x. And that works at every time t. Okay, so here, notice that our displacement is bouncing between x and minus x max and minus x max. Our acceleration is bouncing between omega squared x max and minus omega squared x max. Okay, so on Friday you'll have a quiz over this, but I want to just quick look at a question here, quiz style question. It says a steel ball is hung from a vertical ideal spring which oscillates, where it oscillates in simple harmonic motion with an amplitude of 0.157 meters. So that's our x, m equals 0.157 meters, and an angular frequency of pi radians per second. So that angular frequency is the omega equals pi radians per second. Okay, which one of the following expressions represents the acceleration in meters per second squared of the ball as a function of time? Well, our x is equal to our x is equal to the amplitude x max times the cosine of omega t. Our v is equal to minus omega x max times sine omega t. And our acceleration is going to be, we take the derivative again, and we get minus omega squared x max cosine omega t. All right. So if we wanted to put in numbers here, our acceleration would be minus, and then omega here would be pi over seconds squared, and then our x would be 0.157 meters. And then we'd have cosine of pi over seconds times t. And if we put in the numbers and leave off the units on that, I believe this would give me minus 1.55. That's 3.14 times 3.14 times 0.157, and then cosine of pi times t. Okay, so let's see, is that one of my answers? Minus 1.55 cosine pi times t. All right. So this is just an application of this link, where if we know the displacement as a function of time, we automatically get the velocity and acceleration because we can just take derivatives. Now, one thing that I think is worth pausing a little bit over is, how does this function change as we change that thing? That's your phase offset. And it essentially tells you what is the phase that you get at time equals 0. Okay, so if our phase offset is 0, then this cosine function would just look like this. It would give us our x max. That's where we start at half of our period. We're going to go down to minus x max. And then at our period, we're going to come back. Okay, and you know, we've got a sinusoidal function, so it's just going to keep on doing that. Now, what happens if we choose, for instance, pi over 2? Or maybe I can label this a little better. So this phase, this is 0. The thing that is going into the cosine that gets us to be at a 0 is this phase is pi over 4. The thing that gets us to our minus x max, the phase right there, is pi. Whoops. This should be pi over 2. Right here, we're back to 0. That is 3 pi over 2. And then once I've completed one complete oscillation, that is 2 pi. Now, if I put in a different number in as my phase offset, that means that I get to start at a different point on this oscillation. It doesn't change anything else if we keep our omega the same, but it changes where we start. So for instance, let's say we start at pi over 2. Okay, so everything else about this function, my x max, my minus x max, that's all going to be the same. But what changes is that now, instead of starting out at my plus x max, I would start out at pi over 2. And then the rest of my cycle would go on as normal. Okay, so I'm going to try to draw in these. Okay, so I would go, and everything is going to be offset by that extra. So instead of meaning my minimum, my minus x max, I would go to 0 here, and I would go to my plus x max earlier, and then I would go down to here. Now, of course, you will recognize that what happened here is that I turned this into a minus sine function. But that's okay. We know that our cosine and sine are basically the same, just shifted. Let's try another one. If you decided to go your phase at pi, that would just mean that instead of starting at pi over 2 like we did last time, we'd start here. So we would start at our minus x max and then end up at minus x max. Okay, so here we would go to x plus x max. That'd be halfway through our cycle, and then, oops. All right, so I'm pointing this out because sometimes when people want to graph this, they think that if they add a phase, it should move something to the right, but in fact, it moves it to the left. So it's just a little confusing, but it makes sense if you think it through. So for instance, right here, here's a homework question that I gave you. It says you are to complete figure 1522a so that it is a plot of velocity v versus t for the spring block oscillator that is shown on 1522b for time equals 0. Okay, and then it says in figure 22a at which lettered point or in what region between the points should the vertical v-axis intersect the t-axis. For instance, should it intersect at point A or maybe in the region between points A and B? Okay, so to do this is our v. Just to be clear, this is our v versus t graph. All right, and what this is telling us is that we are going back and forth and back and forth and back and forth. And here, in if we draw out our traditional x versus t. Okay, this is with no phase offset. So there is my pi, there I am. I would consider that to be 2 pi. That's my phase. These are different times. The actual time here would be t, but the phase is 2 pi. Okay, now the v that goes with this would be something like this. It would be, here you're going backwards, so you would be, your graph is flat at the beginning, and so it looks like a minus sine function, like this. All right, now in this case, you are going forward. So that means that you're already in this range. And let's see, does it give us any extra example? Okay, should it intersect at point A, maybe in the region? So if I had to guess, here we're kind of halfway through we're past time equals, we're past the position x equals 0, so we're somewhere in this region. Okay, so if you're looking at this here, it appears that our v is going, so here we're going to be somewhere between d and e, because our velocity is positive, we're going forward, but we are past 0, so we are going to be slowing down. Okay, so for A, you're going to be between D and E. Okay, somewhere in there. And then for B, it asks if the block's velocity is given by that. So that's our standard way that we give it. Here's our x is our x max cosine omega t, and our v is minus omega x max sine omega t plus a phase. So in both of those cases we have plus a phase. And so what it's asking is, if the block's velocity is given by that, what is the value of phi? And it says make it positive, and if you cannot specify a value, then give a range of values. Okay, so if we're looking at this x is 0, pi over 2, pi, 3 pi over 2. These would be the different shifts that would bring this t to 0. So I am looking at this and saying that our v would need to be in this range right here. So our phi would need to be between 3 pi over 2 and 2 pi. Okay, so I know these are a little tricky to think about, but it is worth slowing down and making sure that you understand it. So this one's a little bit tricky. Remember, if you add a phase, it moves your plot right. If you subtract a phase, it moves it to the, if you add a phase, it moves on your x versus t plot, it moves it to the left, and if you subtract a phase, it moves it to the right. So that's a little confusing here. So for instance, in this case, it says, for the 3 simulations, the displacement x versus t for a pair of simple harmonic oscillators A and B. So A here is the solid line, B is the dashed line, are identical except for phase. For each pair, what phase shift in radians and degrees is needed to shift the curve for A to coincide with the curve for B? Of the many possible answers, choose the shift with the smallest absolute magnitude. Okay, so we have to shift A, we would have to shift it left by half by 1/2 of a cycle, and that would put it on top of B. And here it looks like for B I would have to shift right by 1/4 of a cycle, okay? Because the up down is just half of a cycle, so this would be 1/4 of a cycle. So in this case, 1 full cycle, remember, is 2 pi. So for A, it would be a phase left is positive, so it would be 1/2 times 2 pi. Okay, so this would just be plus pi. And then for B, we're going right, so right would be a minus, and so the phase would be 1/4 of the cycle, 1/4 times 2 pi, and since it's right, we're going to have to put a minus on there, and so this would end up being minus pi over 2. Okay, and if you're curious, this could also be written as plus 3 pi over 2 because you go around that circle and it repeats every 2 pi. So this is 0 pi over 2 pi 3 pi over 2. But this is also, and this is of course 2 pi, but this is plus or minus 2 pi, and we could, so we went around the circle counterclockwise, but if we went around the circle clockwise, this would be minus pi over 2, this would be minus pi, and then this one would be minus 3 pi over 2. Okay, so yeah, phases are tricky. Now, one of the systems that we went over in the last video is this block and spring system, where the only forces in the x direction are being applied by the spring, and we saw that the acceleration for a simple harmonic oscillator is just related to the position as minus omega squared times x. And so then if you put in your f equals minus kx into your f equals ma, then you had your minus kx equals m times minus omega squared x. And then you could solve that for omega as square root of k over m. So these are the two things that determine the frequency of your spring is k, this quantity in newtons per meter that tells you about the stiffness. The bigger that number is, the more stiff your spring is. A stiffer spring will have a faster frequency, so it will have a smaller period. And then if you have a bigger mass, bigger the mass, the slower the frequency, the larger the period. Okay? So we do that in lab this week. I want to put one extra wrinkle in this picture of the simple harmonic oscillator. We know that if we have a force, we can calculate how much potential energy we're storing by applying that force, by putting a minus f dot dx. Okay, so like say that we're stretching it from 0 to a position of x. Then in that case, our energy that we would get out would be minus 0 to x. And if we put Hooke's law in here, minus kx dx, what we would get out is just 1/2 kx squared. So this spring, when you stretch it out, holds some potential energy. And if you know the size, what that x looks like, remember our x looks like x max times cosine omega t plus a phase, then our x squared would look like x max squared times cosine squared of omega t. And just remember, all this means is you take cosine omega t and you square the whole quantity after you already put this the argument in. And so if we want to find the potential energy held in that spring at any moment, it would just be 1/2 kx squared. So that would be 1/2 k times x max squared times cosine squared omega t plus whatever phase you start out with. Now, because we know the kinetic energy, the position versus time, we also know what the velocity versus time is. And the velocity versus time is just the derivative of x versus time. So it would be minus omega x max sine omega t. And then if you take the square of that, it would be omega squared x squared sine squared omega t. But since we know that this omega squared is just going to be k over m. If we take the kinetic energy, that's 1/2 mv squared. That would be 1/2 m times k over m. So that would just be 1/2 k x max squared times sine omega t. And this should be sine squared. Now, interesting fun fact is that cosine squared of whatever plus sine squared of whatever equals 1. And that works regardless. You can put any argument in there and it is true. Now, what this means is that if I take this U plus K, the potential energy plus the kinetic energy, cosine squared plus sine squared will give me 1. And so my total energy is always at every single moment going to be the same. So what's happening here is that as your block goes back and forth, your energy types flip back and forth. You go from having all potential energy, no kinetic energy, to having some kinetic energy, some potential energy, to having all kinetic energy when the object goes through 0, and so you're flipping through these different types. All right, so for instance, here it asks, here's a homework question that I gave you. It says, when the displacement in a simple harmonic oscillator is 1/2 the amplitude, what fraction of the total energy is kinetic energy and potential energy? Now, you already know what the total energy is going to be, all right? From our last slide, that total energy is just going to be 1/2 kx max squared, okay? So E equals 1/2 kx max squared. And then it asks, when the displacement of your simple harmonic oscillator is 1/2 the amplitude. So our x is going to be 1/2 of x max. In that case, our potential, it asks what fraction of the total energy is kinetic energy and potential energy. Well, it's easy to find out what my potential energy is because it's just 1/2 kx squared. So it'd be 1/2 times k times 1/2 x max squared. Okay, so 1/2 times 1/2 is 1/4. So this would be 1/4 times 1/2 kx squared. This would be 1/4 of the energy. But if U is 1/4 of the energy, then K must be 3/4 of the energy because they have to add up to be the total energy. Okay, so I'm going to let you think about C here. If you have problems with it, please bring it in on Friday, and we will go over it at that time. Now, the other one that we went over on Monday was the question of pendulums, and we showed how if you work this all out with our angular laws of motion, we could find out that the period of a pendulum, so this is the period for a spring, this is our period for a small amplitude pendulum. The period for the pendulum, it turns out the length is the thing that determines that period. So for the mass matters for the spring and for the spring system. It turns out to cancel out for the pendulum. So that was a bit of a surprise. So in this question that we looked at in our last video, if you start out with a mass of a block and a pendulum, if you start out with them having the same period, and then you switch out the mass such that the mass is doubled, well, you would see that you'd have a period that would go up for the pendulum, for the spring and block, but which would be unchanged for the pendulum. So since the period increases, the frequency decreases. So the frequency of the block would decrease, the frequency of the pendulum would be unchanged. So we discussed that in our last video, but I just wanted to make sure that we hit it again. Now, what are some good applications of simple harmonic motion? Well, perhaps the best one is that of planets and moons. Okay, I need to pause quickly. Okay, we are continuing on with our applications. So, an interesting application is that if you look around at a object moving around in a circle, or I suppose I should go around, actually I don't know which way you're going to see me in the video, but I'll draw it. If you're going around like this, counterclockwise, and you're just tracing around the same circle every time, you can describe the x position in terms of a cosine, the y position in terms of a sine. And so this circle that you're making around and around and around, if you look at it from the side, either from the x side or the y side, it's going to look like an object that's just going back and forth and back and forth and back and forth like a simple harmonic oscillator. So the x squared plus the y squared there will give you some amplitude, and it's interesting because you could even think of these as looking sort of like the potential energy and kinetic energy in our last example. There's a lot of these kinds of close convergences between our different descriptions. Of course, this is important in science history because of the way that Galileo made his observations of Jupiter. Here you can see he's going day after day after day. In fact, sometimes looking a couple times a day, looking at where the moons of Jupiter are, and he sees these little dots and records where the dots are. And of course, he is not sitting at his telescope every minute of the day. You know, if you trained a computer on this thing, you could do that. In fact, if you look it up, you can find videos of this now. But essentially, what he realized is that these dots were going back and forth and back and forth, and what this really was is that he was seeing them going around Jupiter, but he was just seeing it from the side. So he only sees the movement of the dots, back and forth, but he realized that this could in fact be circular motion. Now, when you apply harmonic oscillators to real systems, I should emphasize, there's often you're going to have to think about friction. So in your book, they give you this example where instead of just having a mass and a spring, you might have a damping fluid down here where dragging that press through the water causes this thing to have some viscosity. But in general, if you want that system to die down, if you want, instead of just a x versus t that looks like this, a sinusoid forever, if you want it to kind of go like this, where it starts to die down, do that. That's going to be a much more realistic modeling of your system. And the way that you do that is by adding in an extra force that's sort of depending on V. And so if you have your F equals ma, looking at this, our initial F was just our minus kx, that was our Hooke's law, And then if we can put it in an extra thing that's dependent on v, we would have minus v dx dt equals, and then ma, a remember is d squared x, the second derivative of x. So here we have a system that we can solve. We can look for differential equations that solve it. In fact, what happens is that you get an extra exponential term out front that dies down exponentially related to how big of the b is. If b is big, it dies down quickly. Otherwise, it can die down slowly. Okay, so two things happen. You get the exponential decay, and you get a slight shift in the frequency. The b squared over 4m squared comes out. So if you enjoy that type of thing, I recommend that you check for yourself that this works. You can stick this x into that differential equation and see that it in fact satisfies what we need it to satisfy. Now, an interesting extra piece is that sometimes you can have a damped harmonic oscillator that you drive from the outside. So in addition to having that, that minus kx minus b dx dt, equals your mass times acceleration. Okay, this is what we had last time. What happens when you put in an extra force as a function of time? Well, it turns out that what happens is that if you put a force that's sinusoidal, it's kicking your system, it will inevitably cause the system to sort of oscillate at the frequency that you kick it. But it turns out that there are very specific sorts of phase and frequencies that work better than others. So you can see this at a park. You can do this if you kick your if you push your cousin, or for me it's pushing my kids on the swing set, there's a phase offset of a quarter cycle between when you should push and when the kid is at their maximum. So that's an interesting sort of thing that you can investigate with this. Another interesting thing that you can investigate is the possibility of resonance. Resonance is where you get the biggest possible amplitude out for your input force. Okay, and we are going to investigate this more for the LRC circuit in 2 weeks, so I am going to leave that for then. Now, this can lead to disasters, and if you're interested in seeing this, one very famous example is the Tacoma Narrows Bridge, where the wind goes back and forth, and it pushes this. And I understand now that engineers say that there's a lot more going on than just resonance, but it is sort of an interesting example of how when you get these repeated pushes, it can lead to disaster. So this is a very dramatic video if you look it up, Tacoma Narrows Bridge, where it essentially started oscillating at these modes and tore itself apart. Okay, now, why have we been talking so much about the simple harmonic oscillator? Well, I'll tell you. The reason is a wave looks like an oscillator at each point in the medium. Now, I'm calling waves a new idea, but you've seen waves before. You've seen them in water. These are sort of, you have mechanical waves in the ocean, or earthquake, the earth shaking. We also are sort of familiar with light waves, and really the thing that we're going to see distinguishes waves is that you get these maxima and minima, where the maxima are are where you get the waves adding together, and the minima is where they are subtracting. So you have constructive and destructive interference. And it turns out you can also do this with matter. You can do this thing with things like electrons or neutrons or whatever, and take an electron and essentially split it apart and have it come back together and interact with itself, and that will cause, if you take enough electrons, if you look at one single electron, it just shows up in one place, but there's sort of a probability or quantum mechanical character to that object that allows you to find the wave-like interference if you look at enough of them. So in each of these cases, waves involve the movement of energy through a medium. In this case, the energy is moving through your, the water. Here, the energy is moving in the electromagnetic fields. And then in this case, it's a little questionable. What is the energy moving through? I guess the quantum wave function. Okay, just to say some general things. Hopefully you've seen this before, where you have transverse and longitudinal waves. A transverse wave is where the object is moving in a direction, the wave is moving in a direction. It's propagating. You can see this bump moving along the string. But as the bump is moving this way, the disturbance of the medium is perpendicular. So that's called a transverse wave, like a light wave or an earthquake S wave. But you can also have longitudinal waves. Sound waves are a good example. Earthquake P waves, and that is something that the medium gets disturbed in the direction that the wave is moving. I think a better visualization of this is these types of waves in a slinky. So this is a longitudinal wave in a slinky. It's the compression is moving in the direction of its own motion, and then we can also have a transverse wave in a slinky where you have some equilibrium position in the y direction. The object is moving along x, and so this is a transverse wave. Now, the description of waves is going to be very similar to our description of a simple harmonic oscillator. So if you're looking at this, it looks almost the same. It's got an amplitude. Again, the amplitude is just how it's not the maximum minus the minimum. It's half of the total displacement. So this wave is going up and down like this. The amplitude is 1/2 of that. It also has a frequency, and the frequency is if you look at a single point on it, essentially how long does it take for the wave to pass? Okay, so you're also going to have a period. You're also going to have an angular frequency. So all of that looks the same. How many waves pass every second would be your frequency. 2 pi times the frequency would give you your angular frequency. Your period and frequency, are still, frequency is 1 over the period. Okay, the real difference between our description of a simple harmonic oscillator and a wave is that now, instead of just having one point that's going up and down, now we have a spatial element, and that is the wave length. So it's the distance between one peak and the next peak, or one trough and the next trough of the wave. It is not the distance between the 0 and the 0. That's half of a wavelength. So in the description, we have one extra thing. So we already introduced an angular frequency, which was 2 pi over the time it takes for one wave to pass. Now we introduce the concept of a wave number, and that is 2 pi over the wavelength. So that has units of inverse meters, 1 over meters. Or I guess the radians per meter, in the sense that we're going to be putting it inside of the argument of a sine function. Now, if we look at the description we have of a wave versus the description that we have of a simple harmonic oscillator. So here's our simple harmonic oscillator. Here's our wave. This is just a wave in one dimension, but it now the confusing thing is that we've got a y and an x, but it's moving along the x direction. Okay, so inside of here, if you take a bunch of snapshots, so here's t equals 0, here's t1, t2, t3, t4, where the time is increasing. So time is going like this. You can look at one of these crests and it will appear to be moving in the plus x direction. Okay? If you wanted it to be in the minus x direction, you'd have to put a minus k value in there. But the way that it's written, if you put a positive k in, you're going to get a wave that's moving in the plus x direction. Now, the thing to realize is that this is a function of x and of t. So this function is giving you the value at every single point on that line. This, when we were, so each one of these graphs is not a graph of time, it's a graph of position. And we're taking a snapshot at a particular time. If you wanted to take a snapshot at a particular position, let's say, as a non-random example, we wanted to take a snapshot at our x equals, let me make sure that I have my example right. Let's say I wanted it to be at k over 2. Okay, what does that mean? That means I'm just going to take the snapshot where this is where I'm looking at t equals 0. Well, at that point, my y would be y max times sine, and then this would be just me looking at one point. So look, what's happening at that single point on the string, or whatever what kind of wave this is it's going down, and then it starts coming back up, and then it reaches its maximum again. So this is one full cycle of the wave, and if we look at that particular point, whoops, not x equals k over 2, it would be 2 over k. That would be something with units of meters. 2 pi over k. Then, wait. Third time's the charm. Pi over 2k. All right. Then I would get k times pi over 2 minus omega t, and then this would turn it into, over 2k. So what am I doing here? I'm putting in a particular x. Then this term just allows me to say that this is going to be y max times sine of, k would cancel out, pi over 2 minus omega t, which it turns out is the same as y equals y max times cosine omega t. So what the thing I'm trying to point out to you is that at each one of these points on the wave, it looks like an individual harmonic oscillator. It's going up and down and up and down and up and down and up and down. But what we're doing instead here is we're tracking where the bump is. And what the bump is doing is that it's moving from left to right. It's moving in the plus x direction. So we're tracking the flow of energy through that object in a sense. Okay, and so that's what we're going to have to think about in future episodes of this series. But what have we talked about today? We've talked about how a simple harmonic oscillator trades off kinetic and potential energy. We've talked about how the simple harmonic oscillator can be made more realistic by adding in damping and thinking about an external force that can meet a resonance condition. And then last off, we're going to extend this model of the simple harmonic oscillator to spill over into the description of waves. All right, thank you. See you in 2 days.